Okay, great. So the last thing we're going to talk about today is going to be the return to labor in the short run. So an important point here, right? An important way that our analysis of production is going to vary from our analysis of consumption is that we're going to assume that in production, timing matters. In particular, we're going to make the assumption that firms can adjust their decision about how much labor to hire on a shorter term basis than they can adjust their decision about how much capital to hire. So this might make sense, for example, if we think that capital is going to be things like factories or land, right, or leases for property. We might not be able to build a new factory immediately when prices or production technologies change, but we might be able to hire or fire workers on a shorter time frame, right? Ranging anywhere from maybe we decide how many workers to bring in today on a day-to-day basis, to maybe we decide how many workers we're going to hire on a month-to-month basis, right? It might take a little bit of time to hire and fire workers, but less time than it will take to construct a new factory or get out of our lease or one of these other larger decisions about capital. So we won't be super specific about what these timeframes are, but we'll describe as the long run the time frame under which we can adjust capital, we can adjust capital and labor, and the short run as the time frame under which we can only adjust labor. Right, so if we're a car parts factory, maybe we can renegotiate our lease on our building every year, right? So that'll be the long run. And we hire workers on a day-to-day basis. So a day is going to be our short run. Cool. Okay, so what we're going to do, right, on the basis of this, is we're going to think about, under circumstances under which capital is fixed, right, so in short run circumstances, how is additional labor going to affect our output, right? What are the returns to labor in the short run? So let's start out, let's imagine that we've got a production function, like f of KL, f of LK. It's going to equal, let's say, k to the 1/2 times L to the 1/2. Right, so we're going to have a Cobb-Douglas production function. In the short run, let's imagine that we have k equal to 9. Right? So in that case, right, because of the fact that on a day-to-day basis we can't build or expand or contract our factory, right, we effectively have a production of L and 9 equal to 9 to the 1/2, L to the 1/2, or if you prefer, 3 times L to the 1/2, right? Cool. So if we wanted to, right, we could graph the amount of output we would produce given that we're stuck with 9 units of capital at any given quantity of labor, right? So we make a graph, we've got labor, we've got quantity, right? And we could say something like, you know, obviously when we've got 0 units of labor, we'll have nothing produced. If we have, let's say, 1 worker hired, we would produce what? 3 times 1 to the 1/2 is 3, right? If we hired, let's say, 4 workers, right, we would be able to produce 6 units of output, right? If we hired 9 workers, we would be able to produce 3 times 9 to the 1/2 is 9 units of output, right? So we would have a picture that looks something like this, right? Where we've got output, we've got units of labor. So an important thing to note here, right, is that first of all, as we add more workers, given this production function, right, we're always going to be adding more output, right? We can produce more workers with 9 units of output, or 9 units of labor than with 8. We would produce more with 10 than with 9. But you can notice that the slope of this graph is becoming less and less and less steep, right? In other words, the effect on output of adding a 9th worker is a lot smaller than the effect on output of adding a 1st worker, right? Our first worker produced more additional output than our ninth worker. And we'll call this diminishing marginal returns to labor. And note, right, this is going to be in some ways familiar, right? This was true when we had Cobb-Douglas utility functions as well, when we talked about the amount of one good we'd be willing to give up for the other good. Except in this case, because our production function represents an actual thing, quantity, right, we can say in a meaningful sense that forgetting about comparing labor to capital, right, the productivity of labor to the productivity of capital, we can talk directly about the productivity of labor and argue that the productivity of labor is falling. We can think about this more concretely, more specifically, by defining the amount of output produced by each additional worker as the marginal product of labor or the MPL. We'll say the MPL of L, right, evaluated at LK, is going to be essentially the change in quantity that results from a change in labor, right, dQ/dL. So we could say, for example, the marginal product of our first worker is 3, right, because when we increased our quantity of labor from 0 to 1, we increased our output from 0 to 3. Right, our marginal product of the ninth worker is an increase from 3 times 8 to the 1/2 to 3 times 3, which is going to be much, much smaller. Cool? Now, of course, just like when we talked about marginal utility, right, of one good or another, we're going to want to think not just about the marginal product of a whole hour of work, but of smaller and smaller increments of hours of work, right? We don't just want to know whether the first hour of work was worth it. We want to know if the first hour, if the first second of the second hour of work is worth it. And so we're going to be able to define this, right, for very, very small changes in output using calculus as the marginal product of labor evaluated at L and K equals the change in output, right, the marginal change in output with respect to a marginal change in labor, which, because Q is just equal to our production function, right, is the same as the derivative, the partial derivative of our production function with respect to K, with respect to L. Cool? Right, so essentially what we're saying the marginal product of labor, equivalently the marginal product of capital, is just going to be the partial derivative of our production function with respect to labor. And so in this case, right, we can take the partial derivative of f of L and K with respect to L, which would be the derivative of K to the 1/2, L to the 1/2 with respect to L, would just equal K to the 1/2 times 1/2 L to the minus 1/2, right? Or if you prefer, K to the 1/2 over 2 L to the 1/2. So what this is going to tell us, right, is that indeed we're going to have diminishing marginal returns to labor because of the fact that our marginal product of labor is getting smaller as L increases, right? So we can define our diminishing marginal returns as MPL decreases when L increases. Or if you prefer to think about it this way, right, we can think about it as the second derivative of our production function being negative with respect to L, right? The rate at which our output increases decreases as we add more L. Intuitively, the reason we might expect something like this to happen, right, so we've got our farm, we've got our tractors, and we've got our workers, we've got our factory building, and we've got our workers. As we're cramming more and more and more and more workers into the same factory or into the same number of tractors, each additional worker is going to be a little bit less effective, right? There's not as much to do, there's not as many tools to work with. Potentially people are elbowing each other and getting in each other's way. Okay, so this is very nice, right? This is a very useful thing to know. But in practice, right, if you're a real business, it can be very difficult to estimate your marginal product of labor. It can be hard to know how much each additional worker has contributed to your total output. So what if we wanted to estimate, take a guess at our marginal product of labor by looking at our average product of labor, right? In other words, what if we just said F of LK divided by L, right? So let's just say we said output per worker is going to be our estimate of the amount that each worker contributes to output. Well, let's imagine we wanted to take the average product of labor when we had 4 workers. Essentially what we'd be doing, right, is we'd be dividing the total output, 6, over the total number of workers, 4, which means we would essentially be calculating this slope, right? Output divided by workers. Is that going to be, I didn't draw that well. Right, that slope. Is that going to be higher or lower than the marginal product of labor when we have 4 workers? In other words, are we going to overestimate or underestimate the actual amount that this 4th worker produced? Think about that for a second. So when we have diminishing marginal returns, like in this case, this is going to have to be an overestimate, right? If we thought about how much is that 4th worker producing, the slope of our graph at 4 is going to be significantly less, right, than our average. And the reason is we're going to be averaging together this person's output with the output of all of these previous workers, each of whom was a little bit more productive than the 4th worker. Right? Not because the 4th worker is a schmuck, right? Just because we're getting more and more crowded inside of our factory. Right? So when we have diminishing marginal returns, this is the average product of labor, with diminishing marginal returns, right, our average product of labor, calculated at some specific value, is going to be greater than our marginal product of labor. Right, because of the fact that we're taking the average of a bunch of more productive workers and worker L. That's got to be more than the production of worker L themselves. Okay, great. So we've gotten ourselves, right, to a function for our marginal product of labor, a function for our average product of labor. Right, both of these are going to be essentially upside down parabolas, right? They're both going to be quadratic functions that we expect to increase for a while and then decrease. So let's graph these and talk for a minute about what they ought to look like. And I should say the specific numbers here are going to be less important than the overall shapes. And we're going to talk for a minute about the shapes. To make this simpler, let's just set k equal to 1 for now, so that we don't have to worry about it. Right? Cool. So if we start with our marginal product of labor, right, we know that that's going to be 0 when we don't have any workers. And we know that it's going to be 0 again, right, at some point, which is going to be, right, we could calculate this if we wanted, but it's going to be at 8, right? Because 8 times 8 minus 8 times 8 has to be 0. Right? So it's going to go from 0 to 8. And we know that it's going to have its maximum, right? It's going to have its peak, where the derivative of this thing is equal to 0, right? So where 8 minus 2L is equal to 0. In other words, where L equals 4. And again, I'm blowing through calculating this thing because I don't care that much. Right? So we're going to end up with a shape like this, right? With a maximum at 4. Cool. And then how about our average product of labor? That's also going to be 0, right? When we don't have any workers. And we're also going to have, right, a function that's increasing and then decreasing. Where is it going to hit its maximum? Well, again, where this derivative is 0, right? So where 4 minus 2/3 L equals 0. In other words, where L equals 6. Now, I drew this here, where APL equals MPL at 6. And that's in fact going to be the case. Right? If we want to set average product of labor equal to marginal product of labor, right, we would say 8L minus L squared equals 4L minus 1/3 L squared, right? So I could say then 8L minus 4L equals L squared minus 1/3 L squared, right? So this is going to be divide everything by L. So I'll say 4 equals 2/3 L. L is going to equal 3 house times 4 equals 6. Right? So this is going to be the basic shape that we have. Average product of labor is going to be below marginal product of labor. Up until a marginal product of labor of 6, right? Up until an L of 6, at which point average product of labor is going to be above marginal product of labor. And also average product of labor is going to start decreasing. So I want us to think about a couple things here. Is it a coincidence that average product of labor starts decreasing once it's above marginal product of labor? Why would that make sense? Think about that for a second. So if we think about what's happening, right, when we calculate our average product of labor, essentially what we're doing is we're saying, what's the average productivity of everyone up until the last person that we hired and that last person that we hired? When marginal product of labor is above average product of labor, that very last person that we hired is above average, right? They produce more than the average of everyone before them. So if I add an above average person to an average, I'm going to end up increasing my average, right? If we took the average height of our class and then Anthony Davis joined the class, right, it would increase the average height of the class. So as long as marginal product of labor is greater than average product of labor has to be increasing. And for the exact same reason, right, once marginal product of labor falls below average product of labor has to start decreasing. Does this make sense? Cool. Now another thing that's important to notice, right, is in a case like this, average product of labor is changing more slowly than marginal product of labor, right? If we wanted to calculate the contributions of each additional worker, those contributions increase faster when we have increasing returns to scale, and decrease faster once we have decreasing returns to scale, right? Whereas average product of labor increases less quickly and then decreases less quickly. As a result, it's actually very important to remember this distinction between average and marginal. Because if you were a firm, right, and you were deciding, is it worth it to hire an additional worker? Let's say that you estimated the value of a worker, right? Let's say that you had 8 workers, and you wanted to estimate the value of hiring an additional worker based on average product of labor. You would end up saying that an extra worker is pretty worthwhile, right? They're going to produce a decent amount of stuff. Whereas in reality, that 8th worker is actually worse than useless, right? They're going to get in everybody's way. So I'll leave you with this last thing. This problem of trying to calculate the marginal product of labor, or the marginal product of any input, is one of the most important problems that businesses hire economists to solve. So this can be a little bit abstract and esoteric, right? But it's possible that you'll make a living doing this for the rest of your life. Okay, so I'm going to leave you with this. Thank you so much for sticking with me, and I'm looking forward to talking to you about this soon.